Hello, everyone. My name is Doina Prikop. I'm a professor at McGill University and the Mila AI Institute, and I lead the DeepMind research team in Montreal. Today, I will be talking to you about reinforcement learning. Reinforcement learning is learning from interaction with an unknown stochastic environment. It is inspired by theories of animal learning. For example, in this little picture, you have a mouse that is learning how to push a sequence of levers. If it pushes the correct sequence of levers, it is rewarded by a food pellet. We mimic this process in artificially intelligent agents by taking software agents, putting them in an environment. The agent is allowed to perceive the state of this environment and take actions. And as a result of these actions, the agent gets a reward, which is a number. And the goal of the agent, loosely speaking, is to maximize the total reward that it receives over time in expectation. And what we're going to talk about is algorithms for achieving this goal. Reinforcement learning has developed at the intersection of several different disciplines: computer science, neuroscience and psychology, economics, where concepts like bounded rationality have arisen, and of course, mathematics and engineering. A lot of modern reinforcement learning is actually the result of a blend of ideas from reward systems and classical conditioning with formalisms from operations research and optimal control, machine learning ideas as well. Broadly speaking, reinforcement learning agents are driven, just like all of machine learning, by minimizing prediction errors. The special thing about reinforcement learning is that the algorithm makes predictions about the expected future cumulative reward, and so it tries to minimize the predictions that it's making over time. What this amounts to is to make sure that these predictions are consistent with each other from time step to time step, and we're going to formalize this notion of consistency in a minute. It basically means that we're going to compute errors between predictions made at consecutive time steps, and as an additional ingredient, we're going to have the agent pick more often the action that appears to be best. As a computational framework, reinforcement learning typically relies on discrete time steps. So you imagine that a clock ticks at time step t, the agent perceives the state of the environment. Based on this perception, it's going to choose an action. The action will cause the agent to receive a numerical reward. And the goal of the agent is going to be to find what's called a policy. In other words, a way of choosing actions that maximizes its long-term expected return. We're going to define both policies as well as returns more formally in a minute. One famous example of a very successful reinforcement learning system is this program called AlphaGo, which has been developed by my colleagues at DeepMind. In this case, we teach a reinforcement learning agent to play the game of Go. This is a perfect information two-player game where there are white pieces and black pieces on an 18 by 18 board as depicted in the picture. And the goal of the agent is to capture territory. So the perception of the agent is the state of the board in which we encode the positions of the pieces at every corner. +1 might mean a white piece, -1 a black piece, and 0 means there's no piece there. The actions in the game are legal moves for the game of Go, and the rewards are only received at the end of the game. At the end of the game, the agent knows if it's won, in which case it receives a reward of +1, or if the agent has lost the game, it receives a reward of -1. There are no other intermediate rewards to tell the agent what is a good move or a bad move. The agent really needs to experiment, play games in order to decide for itself a mapping from board positions to good moves. How does the agent train? Well, because we need a lot of data in order to understand this complicated game, the agent trains by playing games against itself. In other words, against a copy of itself. And this way, of course, it also receives twice the amount of data for the loss as well as for the win. Interestingly, agents that are trained in this way, as opposed to, let's say, by supervised learning, invent new ways of playing which seem superior to those of people. This is very exciting, of course, because it means our AI agents now have the potential of being better than people at a well-defined task. It can also seem a little bit scary, but from my point of view at least, this is a really interesting way to develop real AI agents. Now let's look at the agent environment interface and try to make our notions a little bit more formal. The agent observes at every time step t a state, which we denote here st, and it takes an action denoted at. As a result, one time step later, the agent receives a reward denoted rt plus 1, and the environment transitions to a next state, st plus 1. So now we can consider a trajectory, which means a sequence of states, actions, and rewards that terminates whenever the episode or the current interaction of the agent with the environment terminates. This termination might be due, for example, in our Go game, to the fact that the game has ended. Now, the first problem that we want to study is that of prediction. In other words, suppose that the agent has already a policy, this means a mapping from states to actions, which is fixed and given. Maybe it's uniformly random, so not very informative. Now we want to predict the future, and the relevant thing that we're interested in is the return. The return is a cumulative measure of rewards. If we want the agent to do things quickly, we also need to communicate this to the agent somehow, and this is done typically by the discount factor. The discount factor, denoted gamma in this equation, is a number between 0 and 1, and it devalues rewards received farther into the future. The economic equivalent of gamma is having, for example, an inflation rate, which devalues the money received by the agent over time. It's also helpful to think of gamma as the probability of continuing the agent's trajectory. The value function of a state at a given time step and given a particular policy is just the expectation of the agent's return. So the expected value of gt given the state s, and given that the actions of the agent from then onwards are drawn from the policy. Now, how do we estimate value functions? Well, value functions are expectations, so the simplest idea that comes to mind is just to sample the expectation. This does not rely on any assumptions about the environment, can always be done. And so we can think of this as the tree of interactions in the pictures where the agent is at some state st. It executes a trajectory where all of the actions are chosen according to its current policy pi. The agent observes the return, gt, associated with this trajectory, and then it can update its value estimate in the direction of this return, according to the equation in the figure. The learning rate or step size alpha is a number between 0 and 1 and tells us how much we want to pay attention to this most recent received return, gt, compared to the previous estimated value function. And this is, of course, a standard way of doing updates to any kind of estimator. Now, we can also assume more structure in the problem. The most helpful structure from this point of view is going to be that of a Markov decision process. In this case, the next state and reward only depend on the current state and action and not the past history. And so when we think of the environment of the agent, we can consider the environment as being fully described by the reward and transition model of the agent, in other words, a probability distribution over next rewards and next states, given the agent's current state and action, as given in the equation. We can exploit Markovian structure by noticing that returns actually have a recursive form, where the return gt at time step t can be written as a sum between the next reward, rt plus 1, and then gamma times the next return, gt plus 1, the return from the next step onwards. So from the value function definition, we can just plug in this equation, and then the Markovian property is going to allow us actually to break up this equation by taking into account the fact that the value of the next state is actually the expected value of the return gt plus 1. And so we obtain a recursive form that relates the value v pi of a current state S to the values v pi at the successor states, the next states, S prime. And of course, other components in this equation are the policy and the environment that the agent is in, the transition of the environment. Dynamic programming for policy evaluation can be considered an incremental version of this equation, as depicted in the figure. So in this case, we take a state st and we can update its value based on our current estimates of the values v of s prime of all of its successors, averaged according to the policy, pi, and according to the transition model of the environment. Compared to our previous Monte Carlo approach, this approach is sort of like a breadth-first search, where the agent from state st is going to consider all possible next choices of action and all possible next states as prime, but then not search any further, because v of s prime is essentially a proxy for the return that would be obtained from s prime onwards. This is in contrast with the depth-first search approach of Monte Carlo, where the agent has to execute a full trajectory, and only then it can update the value of a particular state. How can we combine these two types of updates? Well, the typical approach that we use is what's called temporal difference learning, or TD learning, where essentially we take one step, a sampled step from state st with an action taken according to the policy, landing in a state st plus 1, and then update the value function v of st from this one sample. So from st, we go to rt plus 1 and st plus 1. We're going to take the estimate rt plus 1 plus gamma v of st plus 1 as a target and update the value function v of st in this direction with a step size alpha. Like Monte Carlo, this is a sampled update. It provides one time step as opposed to creating an expectation. And like dynamic programming, this approach bootstraps. In other words, it uses the agent's current guess, v of st plus 1, as a surrogate for the return that would be obtained from st plus 1 onwards. Obviously, this is just a guess, but as the agent gets better and better over time, these guesses will become more and more accurate, and so the targets are becoming more precise. So temporal difference learning is this fundamental algorithm due to Rich Sutton in his seminal 1988 paper, and the idea is simply to use this temporal difference error, the error between the agent's estimate at time step t, v of st, and the agent's estimate one time step later, rt plus 1, plus gamma v of st plus 1, in order to drive the agent's learning. And if the value function is parameterized by some parameter vector w, then in fact we can use this temporal difference error signal to update the parameters w just as we would in supervised learning. So in other words, we can take the gradient of the value function and do this kind of update. Now, obviously, this is not going to be exactly like supervised learning, because the target is a moving target. The agent's value function keeps changing over time, and so from a theoretical analysis point of view, this algorithm actually cannot be analyzed using gradient descent tools, and instead is analyzed using fixed point methods. Interestingly, Schultz, Dayan, and Montague showed in their seminal paper in 1997 that TD errors are a good model for dopamine neurons, and you will explore this much farther in one of the tutorial sessions. The problem with using one-step backups is that they are quite impoverished. They rely a lot on the value of the next state, and also, implicitly, they rely a lot on the Markov property of the environment. But sometimes the environment is partially observable, or maybe we are using an estimate of v that is not accurate because of function approximation. N-step backups or multi-step backups are a way to gracefully interpolate between TD targets and Monte Carlo targets. In other words, we can consider truncating the agent's return, not after a single time step, but maybe after 2 time steps or 3 time steps or so on. The n-step TD target is depicted in the equation. It basically takes the following n rewards and the value of the state at time step t plus n and uses that as a surrogate. And because of the discounting, this value is going to essentially be washed out considerably compared to the original. The infinite step TD is essentially the Monte Carlo algorithm. So the n-step backups provide a trade-off between temporal difference learning and Monte Carlo. As Monte Carlo tends to be high variance and TD is a biased algorithm, this essentially provides a bias variance trade-off, as may be familiar to some people who do supervised learning. Now, we can further interpolate between these two by using eligibility traces. Eligibility traces provide a weighted sum of n-step returns weighted by a parameter lambda. And now lambda is a number between 0 and 1. Lambda equal to 0 gives us exactly TD, and lambda equal to 1 gives us exactly Monte Carlo. This is a very interesting idea, but the sum that you see there that goes to infinity looks a little bit daunting. Obviously, this form of the algorithm would not be something that we could implement in practice. And so instead, what we implement is an incremental version of eligibility traces, where the sort of intuitive explanation of this is that whenever we arrive from state st to a state st plus 1, we have this little person here who computes the delta t, the TD error, and then shouts this error backwards over the entire trajectory. And this error actually gets diminished over time, right? Just like sound would sort of fade away the farther a particular state is to this error. Now, how do we implement this? We implement it using this eligibility trace vector denoted z. This starts initialized to 0, and then whenever a state is seen, that we mark that fact by pushing the eligibility vector up, and then it fades away with gamma lambda, which provides this kind of fading of the error over states that are farther away in the agent's past. If we want to use function approximation, instead of pushing the eligibility vector up at every state, we're going to use the gradient of v hat and put that gradient into the eligibility trace vector. And again, this decays over time by gamma lambda as shown in the figure. So now we actually have a unified view of several fundamental prediction algorithms between dynamic programming, temporal difference learning, and Monte Carlo, with the width of the backup, or the number of actions sampled from a state, trading off between dynamic programming and temporal difference learning, and the height or depth of the backup trading off between temporal difference learning and Monte Carlo. Now we're going to tackle the more interesting problem, which is the control problem. In this case, we want to estimate the optimal policy, the best way of behaving from trajectories. And actually, the algorithms that we use are going to be based on the seminal work of Bellman, who showed that in a finite Markov decision process, there is a unique optimal value function and at least one corresponding optimal policy. The optimal value function over states, v star, is obtained by maximizing the value v pi over all the policies at a particular state S. Now, because we want to facilitate action choices, it's very useful actually to think of a slightly different value function called an action value function denoted q star. Q star allows the agent on the very first time step to consider an action choice, A, that is different from what the policy pi might normally choose, and this is in order to allow the agent to explore its environment and consider alternative actions. And so we're going to talk about some methods for estimating and leveraging Q star. The first approach that we're going to talk about is called value iteration. In this approach, V star of S is computed by maximizing over the agent's actions A. And so again, we can use the ideas from our recursions in order to establish a relationship between the value of a state and the value of the next states S prime. Now, this relationship is usually turned into an update rule, where we will start with some estimates for values, let's say V0 being all 0, and at every iteration k+1, we're going to update the value function of all the states according to the model of the environment, so the reward and transition model, and the value vk of s prime, so the estimated value at all of the states that are currently in use. So just to illustrate visually this process, consider this little navigation environment where we have an agent in a grid world. The agent can move up, down, left, or right. Its actions actually fail with some probability. In this case, they fail 30% of the time, in which case the agent is blown randomly to one of the other neighboring states, not the intended state. And in this case, we have no rewards until the goal is reached. And we're going to use a discount factor of 0.9, which essentially tells the agent that it should get to the goal state as quickly as possible. In the first picture, we see the initial value function, which is 0 everywhere, except at the goal state, which is marked by the black circle. And at the goal state, the value is 1 because the agent finishes the episode and gets its full reward of 1. Value iteration will take this goal value and propagate it backwards through the environment. So on the iteration number 2 of the algorithm, the states that have actions capable of transiting into the goal state are going to get some value, and this value is represented by the smaller circles. And if we want to find a good policy, the agent essentially can move from a smaller circle to the bigger neighboring circle. So it can follow essentially the gradient of these values from smaller value to higher value. And that policy is going to be, in our case, in fact, optimal. The problem is, of course, that the majority of the environment does not yet have an interesting policy. In iteration number 3, these values propagate one step farther. So now states that are capable of reaching the goal in 2 time steps are going to get some value. Their circles are smaller because, of course, they're farther away from the goal. And so as a result, they have smaller associated values. If we continue this process on and on for a couple dozen iterations, finally, the values would propagate through the entire environment. And at that point in time, even though the value accuracy would not be perfect everywhere, the agent would have a perfect policy everywhere, as I mentioned, by following the actions that are taking it to the best neighboring state. Model-based reinforcement learning is an approach which essentially tries to apply the dynamic programming procedure, but using a learned model rather than using an exact model. So we can use this approach whenever the agent is in an unknown environment. The agent can take trajectories in this environment, estimate the reward and the transition model, which here it's denoted p tilde, for example, by using maximum likelihood methods, supervised learning methods. And then we can use dynamic programming with this approximate model. And there are well-established results that tell us how the error in the model relates to the error in estimating the optimal policy and the optimal value function. However, there is a fundamental problem with the dynamic programming approach, which is highlighted here in red. Basically, dynamic programming requires us to consider all possible next states and all possible actions. And that can be problematic if, for example, the state and action space are continuous or really large. In the case of Go, the state space is discrete, but it's of size 10 to the power 170, so it's enormous. And the action space is also very large, about 100 possible actions per time step in the game of Go. And so the agent cannot solve this problem exactly. It needs to sample and use function approximation instead. This is a class of method called model-free reinforcement learning, and in particular right now I'm going to talk about model-free value-based reinforcement learning. In this case, the agent will take trajectories and estimate the action value function directly from these trajectories, and then the optimal policy is simply greedy with respect to this value function q. So AT here is the action that the agent would take at time step t, and the greedy action is just the action that maximizes q of st and a at the state st. Now, in order to learn the values of different actions, the agent actually also needs to explore its environment. So one example is depicted in this picture here. This is an environment called deep sea due to Ian Osband and colleagues. Here you can imagine the agent being a little diver that starts from the ship in the top left corner, and it needs to find the treasure chest. Now, the chest might contain treasure, it might contain a bomb. The agent does not know this information ahead of time, but certainly if the agent comes down to the bottom of the ocean and finds no treasure, then there is no payoff. And so the agent needs to not just always follow its currently best guess, but also to try actions that are currently not optimal in order to learn about them. And this is the process that we call exploring. Exploration methods come in various shapes and sizes, but fall into four basic categories. The first category is called randomization, which means adding noise to the greedy policy of the agent. For example, epsilon greedy algorithm adds noise a small percentage of the time, epsilon. This approach is something that you will actually play around with again in one of the tutorials. Now, in the case of deep sea, randomization doesn't help very much because it's just going to make the agent dither around, possibly not making very much progress. Another approach is optimism in the face of uncertainty. In this case, the agent assumes that essentially any state that it has not yet visited contains treasure, and so it's going to be driven to see all these states. The algorithm that performs this is called UCB, upper confidence bounds, and there are many versions of this algorithm, in fact. However, of course, optimism can also be problematic because it will force the agent to cover the entire environment, and this may also not be sufficiently efficient because the environment might be just too big. Probability matching is an approach that selects the actions according to their probability of being best. Thompson sampling is the poster child of this kind of approach. So, for example, in this case, if the agent has a 0.7 chance, has an estimate that action left is worth 7 and action right is worth 3, then maybe it would choose these actions with 0.7 and 0.3 probability, respectively. Thompson sampling requires the agent to take a Bayesian approach and maintain an estimate of its uncertainty, so it can be more expensive computationally. Finally, the best, but perhaps most expensive approach is Bayes adaptive MDPs, in which the agent actually plans to explore. So in other words, the agent can consider what might happen under different choices of actions, and then it decides what to do. This is, of course, the best approach in terms of sample efficiency, but it is extremely expensive computationally. Very often, randomization is the method of choice due to simplicity, and so randomization is what will be explored in the tutorials here. Now, let's assume that the agent knows how to explore the environment. How can it update the value function, the Q function? There are two main classes of approaches. The first one, called Sarsa, is on-policy learning. In this case, we learn the action value function of the current policy, and so this means that the agent has to act near greedily with respect to the current action value estimates and also take exploratory actions sometimes, and these actions will be taken into account in estimating the Q function. So in every time step, the agent is going to update its parameters W according to a TD error that now contains Q values instead of V values, and it's going to use the gradient of the Q function in order to apportion this error to various parameters, as in the previous cases that we have discussed. And again, alpha is a learning rate or step size between 0 and 1. Q-learning is a different approach that works off of the value iteration equation for action values and essentially uses a sampled version of this, in which the agent is at a particular state ST, chooses an action AT, and then observes the reward, but then imagines that from the next state ST plus 1 onwards, it would do the best possible action, denoted here A prime. So this is an approach called off-policy learning, because the agent is following some behavior policy, which could in fact be, for example, purely uniformly random, but it always imagines the best possible outcome, regardless of what it actually ends up doing. In the tabular case, we can show that this approach actually converges to the best possible outcome, the optimal policy, regardless of the behavior policy, so long as the behavior policy is sufficiently exploratory. This is a very, very strong result. However, with function approximation, most of the theoretical results are negative results. In other words, this approach can cause problems or divergence. Now, you're going to further actually explore the link between on-policy and off-policy learning and the relative behavior of these methods during one of the tutorials. But I wanted to show you some really exciting empirical results that are used with Q-learning, especially with Q-learning and function approximation. So in the work that I'm going to show you, we discuss how Q-learning can be used in very large environments, essentially by using a parametric function approximator parameterized by W here, if the state and action space is large. Imagine W being the parameters of a neural network, let's say. So what we're going to do is we're going to take as inputs the state and the action. We're going to build a function approximator that tries to estimate QW, the optimal Q function, and this estimator is going to generalize from a possibly small number of state-action pairs to other unseen states and unseen actions, and the generalization happens through the parameters W. This approach is at the heart of an algorithm called DQN, which also has been developed at DeepMind, and is a standard approach to solve the Atari games, learning from pixels, so raw images, to predict scores in a game. So in this case, the state space is images on a screen. The action space is actions with a joystick, so there are 18 actions, and the agent learns to estimate the values of these actions, and then it's going to do epsilon greedy exploration, so randomized exploration, in order to figure out how to play these games. And actually, this approach is really, really successful in many games, currently, in fact, all of the Atari games. Now, what is this mysterious function approximator in the middle of this approach? Well, in this case, we need to process images, so we're going to use a convolutional neural network, which is a well-developed, well-accepted way of processing images consisting of a sequence of convolutional layers, in this case of rectified linear units. At the output, we're going to have some fully connected layers that are leading to the Q functions. And the other thing that we need to see here is that because the environment is not fully Markovian in the observation space, we need to help the agent make a more Markovian environment. So what does this actually mean? Well, in a Markovian environment, the agent could rely on just its immediate observation. But in a game, the directions in which things are moving, the speed at which things are moving, is not available from a single frame of the game, and so we need to stack 4 of these frames together in order to allow the agent to have a sense of speed and direction of movement as well. Value-based methods, which we have explored so far, learn the value of each action. Now, what this means is that the policy is sort of implicitly defined by the action values, and specifically by taking mostly greedy actions. There is a different class of policies called policy-based, different class of algorithms called policy-based methods, which learn the parameters of a stochastic policy directly by doing gradient descent on the return. So this, broadly speaking, is what people call policy optimization, and we're going to look at a special case of this approach. All of these algorithms rely on a different dynamic programming approach called policy iteration, where we start with some policy, we compute its value function, we make the policy more greedy with respect to its values, and then we continue this virtuous cycle going between action values to policy and back. Notice that here the policy is parameterized independently of the value function, and so in some cases where the policy is easy to parameterize, this approach can be very, very powerful. This is a sketch of what policy optimization looks like. Unfortunately, we don't have very much time to spend on it, but the idea is that the agent is going to use a parameter vector theta as the parameters of the policy. So policy is now pi theta. For example, the policy might be a Gaussian whose mean and variance are computed as a function of the agent's state. So in this case, mu of s is the mean of a Gaussian policy centered at state s, and the probabilities of different actions would be computed from a Gaussian with this mean, and the variance might be also given by some parameter theta sigma dotted with the feature vector phi s of state s. So in this case, for example, the policy is indeed easy to parameterize, and the action space that it allows us to use is continuous. Now, how do we update the parameters of the policy? Well, we update them in the increasing direction of the gradient of j theta. And so we can recompute this as an expectation, and this now gives us a general approach for doing our updates to the parameter vector theta. The actor-critic architecture by Sutton and Bartow allows us to use both the value function as well as the policy together. So in this case, we have an actor or a policy that's parameterized. There is also a value function which is parameterized independently. Value function is providing the learning signal to the policy, and essentially this learning signal is going to compare the action value of a new action, AT, to the average value of the actions, V of ST. And so it computes a signal which we call the advantage. How much advantage does the action AT have compared to the current policy of the agent? If the advantage is positive, the policy is encouraged to choose this action more often, and if the advantage is negative, then the policy is encouraged to suppress this action. John O'Doherty and colleagues have shown some fMRI evidence that the dorsolateral striatum implements an actor and the ventral striatum implements a critic. Now, in synthetic agents, policy optimization can learn very complex control. So, for example, in the pictures, you see an ant, which is a quadruped walker, which is trained by this approach using advantages and using a neural network as an encoding of the policy in order to walk through irregular terrain and make its way from a start state to a goal state. In this case, there's one further trick, which is again quite standard in the field, which is to use entropy regularization in order to ensure that the policy does not change too aggressively or too quickly. In terms of the comparison between value-based and policy-based methods, one question that I get asked often is which one is better? And the answer really is that it depends on your application. These are like apples and oranges. Both approaches can work very, very well, but they're typically applied to different kinds of problems. Specifically, value-based methods are often preferred with discrete action spaces. Policy-based approaches are often preferred for continuous control. And these days, a lot of the time, we use function approximators inside of both of these types of methods, which are deep networks. And so deep reinforcement learning is the catch-all phrase used to say we're doing some reinforcement learning method with a deep network as a function approximator. Deep networks are very expressive, and they have allowed us to scale reinforcement learning algorithms quite a bit, but we still need to improve the stability of their training and their data efficiency in order for these algorithms to really work very well. I will wrap up here. There are many more interesting topics that we did not cover today, such as making model-based reinforcement learning algorithms with deep network approximators, using temporal abstraction in reinforcement learning, fancier exploration methods, as well as many more links to the biology. And I invite you to see Tim's talk in order to explore more some of these links and some of the frontiers. Thank you very much for your attention.